Okay, 33, a 1024 Hertz tuning fork is used to obtain a series of resonant levels in the gas column of variable length, with one end closed and the other open. The length of the column changes by 20 centimeters from resonance to resonance. So from this data, the speed of the sound in this gas is what? Is E. It's 410. 410 again, because I don't remember. 410 meters per second. So 34, we have a vibrating tuning fork, which is held over a column, a water column with one end closed and the other end open. So as the water level is allowed to fall, a loud sound is heard from water level separated by 17 centimeters. If the speed of the sound in air is 340 meters per second, the frequency of the tuning fork is what? Is B, which is 1000 hertz. 1000, I don't know what thousand pay. So vargadi forok. And then an organ pipe with one end open and the other closed is operating at one of its resonant frequencies. The open and closed ends are respectively B. So respectively pressure nodes and displacement nodes. Pressure nodes and displacement nodes. So an organ pipe with one end closed and the other end open has length L. Its fundamental frequency is proportional to what? To B, 1 over L. In other words, they're saying it's inversely proportional. And then 5 organ pipes are described below. Which one has the highest frequency fundamental? So A 1,6 meter pipe with both ends open. With both ends open is the one that is the highest frequency fundamental. So if the speed of sound is 340 meters per second, the length of the shortest closed pipe that resonates at 218 hertz is what? Is C, is 39 centimeter. So 39, the lowest tone produced by a certain organ comes from a 3,0 meter pipe with both ends open. So if the speed of sound is 340 meters per second, the frequency of this tone is approximately D, which is 57 hertz. So 40, the speed of sound is 340 meters per second. The length of the shortest pipe closed at one end will correspond to a 512 hertz tuning fork, which is approximately C, which is 17 centimeter. So if the speed of sound is 340 meters per second, the two lowest frequency of an 0,5 meter organ pipe closed at one end are approximately B, which is 170 and 510 hertz. And then we have 42, we have an organ pipe Y open at both ends is half as long as organ pipe X K1 So as shown, the ratio of the fundamental frequencies f of x is to f1. So the ratio can be 1:2 since they say it's no, it's not the ratio of the length, but the ratio of the fundamental frequency. It's 1:1, it's still 1:1. I don't know how, but it's not by length it's 1:2, but by frequency it's 1:1. A 200 centimeter organ pipe with one end open is in resonance with a sound wave of wavelength 270 centimeter. The pipe is operating in its second harmonic. And then we go on to 44. So an open pipe with both ends open is 0,85 meters long. Assuming that the speed of sound is 340 meters per second, the frequency of the third harmonic of this pipe is 600 hertz. So the A of the trumpet and the clarinet have the same pitch, but the two are clearly distinguishable. So which property is most important in enabling one to distinguish between these two instruments? It's in harmonic content. Harmony is the pitch. So the halves of a trumpet and the slide of a trombone trombone is you pull it, and then trumpet you just do the notes, but the trombone you pull it. Are for the purpose of changing the length of the A column. The answer is D. Will change out the length of the air content. So two small identical speakers are connected in phase to the same source. The speakers are 3 meters apart and at ear level. So an observer stands at X, 4 meters in front of one speaker shown. If the amplitude are not changed, the sound he hears will be most intense if the wavelength is A, which is 1. The difference between 3 and 4 is 1. So we have two small identical speakers are connected to the same source. So the speakers are 3 meters apart and at ear level. So an observer stands at X, 4 meters in front of one speaker shown. The sound she hears will be most intense if the wavelength is 1. Oh, it's the same question, just that now they like, yeah. The rise in pitch of an approaching siren is an apparent increase in its frequency. Yeah, if it's going to be an apparent increase in frequency. So the diagram shows 4 situations in which a source of sound S with variable frequency and a detector D are either moving or stationary. The arrows indicate the directions of motion, so the speeds are all the same. Detector 3 is stationary. The frequency detected is the same, so you should rank the following. You should rank the following situations according to the frequency of the source, lowest to highest. So B, we're going to say 4, 3, 2, 1. 4, 3, 2, 1. 4, 3, 2, 1. 4, 3, 2, 1. So a stationary source which generates about 5,0 water waves whose speed is 2. A boat is approaching the source at 10 meters per second. So the frequency of these waves as observed by a person in the boat is E, which is 30 Hz. So a stationary source S which generates a circular outgoing wave on a lake. So the wave speed is 5,0 meters per second and the crest to crest distance is 2,0 meters. So a person in a motorboat heads directly towards S at 3,0 meters per second. So to this person, the frequency of those waves is D, is 4. 2 times 2 is 4. A stationary source emits a sound wave of frequency F. If it's possible for a man to travel towards the source at the speed of the sound, you will observe the emitted sound to have a frequency of D, which is 2F. A source emits sound with a frequency of 1000 Hz. So if it and an observer are moving in the same direction with the same speed, which is 100 meters per second. So if the speed of sound is 340 meters per second, so the observer hears sound with a frequency of 1000 Hz. It's still 1000 Hz. So a source emits sound with a frequency of 1000 Hz. It and the observer moving towards each other with the speed of 100 meters per second. The speed of the sound is 340. The observers. Okay, this one you use the formula, but for sake, if they're moving in the same direction, it's going to be 1000. Moving moving towards each other is going to be 1830. It's going to increase. A source emits sound with a frequency of 1000 Hz towards the stationary reflecting speed of sound rest behind 118 Hz. But this one I can calculate on 18 Hz. So in each of the following two situations, a source emits sound with a frequency of 1000 Hz. In situation I, the source is moving 100 meters per second towards an observer at rest. In situation 2, the source is moving at 100 meters per second towards the source with stationary. The speed of the sound is 340. The frequency heard by the observers in the two situations are A, it's 1417, and then Roman figure 21294. 1417, then we minus 2 on the right. The Doppler shift formula for the frequency detected is that whatever. So the answer is B. Vt is equal to 10 meters per second, and then Vs is equal to 8 meters per second. Same as this one, they just took 2 off. A plane produces a sonic boom only when it flies faster than the speed of sound, or a sonic boom if it flies faster than the speed of sound. So if the speed of sound is 340 meters per second, a plane flying at 400 meters per second creates a conical shock wave with an apex half angle of 58 degrees. So the speed of sound is 340 meters per second. So a plane flies horizontally at an altitude of 10,000 meters and a speed of 400 meters per second. When an observer on the ground hears the sonic boom, the horizontal distance from the point on its path directly above the observer to the plane is b 6.2 usually.